Two insulating spheres have radii 0.3 centimeters and 0.5 centimeters, masses 0.25 kilograms and 0.7 kilograms, and uniformly distributed charges of negative 2 microcoulombs and positive 6 microcoulombs. They are released from rest when their centers are separated by 1 meter. How fast will each be moving when they collide? If the spheres were conductors, would the speeds be greater or less than those calculated in Part A? Okay, so this problem gives us two charged insulating spheres. The first one has a radius of 0.003 meters and a total charge of negative 2 microcoulombs and a mass of 0.250 kilograms. And the second one has a radius of 0.005 meters, a charge of positive 6 microcoulombs, and a mass of 0.700 kilograms. And the centers to start are 1.00 meters away from each other. And I drew these force vectors here to show that it's an attractive force because they are an opposite charge and they're the same magnitude. More on that later. So the problem asks us to find the velocities of the spheres right before they hit each other. And you might be thinking, where the hell do I start? But since the problem gave you a nice hint to use the conservation of energy, I knew I had to do something with energy. And the best way I knew how to get energy was using our work equation. Work is equal to the integral of F dx. Except in this case, the force is going to be the electric force. We could put a nice little sub E there. And this means that work is going to be the integral. Remember the equation for the electric force? K times Q1 Q2 over R squared. And you can change the dx to a dr because they're both just measurements of distance. And now I know the K, the Q, and the Q are constants, so they get to come out. So you're left with the work is equal to K Q1 Q2 over the integral of dr times R squared. So this means work is equal to K times Q1 times Q2. And now I have to integrate 1 over R squared. Integrate, you raise the power, goes from negative 2 to negative 1. And you got to divide by the new power, negative 1. And you have to evaluate it. Now I got to decide on some bounds. Well, I'm looking at this problem here. When it starts out, they're 1 whole meter away, so that'll be my top bound. And at the end, when they're touching, the centers are going to be a distance equal to the sum of the radii, which is 0.008 meters. Now I got to plug in these values here. So it'll just be negative 1 over 1 meter minus negative 1 over 0.008 meters. This simplifies down. Negative 1 over 1 is negative 1. Negative 1 over 0.008 is 125. You get 1, negative 1 plus 125. 124, 1 over meters. Now we get to plug in our values of K, Q, and Q. Here we substitute the total charge of a sphere in for Q because the center of the sphere is the center of the charge distribution. We know K is 10 times 10 to the 9 Newton time meters squared per coulomb squared, times the magnitude of charge 1, which is 2 microcoulombs, times the magnitude of charge 2, which is 6 microcoulombs, times again 124, 1 over meters. Put this all into your calculator, you get a value of 13.392 joules. So that looks pretty impressive and intimidating, but this isn't our final answer. It doesn't want the amount of work done by the electric force, it wants the speeds. So we also know that work is equal to the change in kinetic energy. And this is very helpful because the kinetic energy is the final kinetic energy minus the initial. And you know at the initial it's 0. So in this case, the work is equal to the final kinetic energy. You're like, alright, let's expand that because we know what the kinetic energy is equal to. 1 over 2 m1 times v1 squared plus 1 over 2 m2 times v2 squared. And now I got a problem because we have one equation and two unknowns. This is where I said the forces being equal in magnitude are important. I'll come over here. We have the electric force on the first sphere is equal to the electric force on the second sphere. And since we know that force is equal to mass times acceleration, we can substitute the first force with mass 1 times acceleration 1, and the second force with mass 2, acceleration 2. Alright? And now we know acceleration is the change in velocity over the change in time. And we know that due to the different accelerations, the spheres are going to have different amounts of a change in velocity over the same amount of time. But now that we have time on both sides, we get to cancel those out. And now we're left with the mass of the first sphere times its change in velocity is equal to the mass of the second sphere times the change of that sphere's change in velocity. And side note here, this is actually an equivalent statement to the change in the momentum of the one is equal to the change in the momentum of the two. Figure that's kind of cool. So now over here, we could rearrange some variables here and get a ratio for the velocity of the first sphere to the velocity of the second sphere. Since we know that all the spheres are starting with a velocity of 0, we know the change in velocity is equal to the final velocity. So I divided both sides by mass 1 and by the second velocity to get v1 over v2 is equal to m2 over m1. And now we can multiply both sides by v2. We get v1 is equal to v2 m2 over m1. And now we can take that equation and bring it back up into here. So we know our total work is 13.392 joules. I'll factor out the 1/2. We know the mass of the first one is 0.25 kilograms. And we know that the velocity of the first sphere is equal to v2 times m2 over m1. M2 is 0.7 kilograms. M1 again is 0.25 kilograms. Except both of these mass terms are squared, so we have to square both of those. Coming down here, we know the mass of the second sphere is 0.7 kilograms. Again, times the second velocity squared. Multiplying both sides by 2. We get 26.784 joules is equal to, you got a 0.25 kilogram up here and a 0.25 kilogram squared down here. So one of those will cancel out. And then again down here we have plus the 0.7 kilograms times the second velocity. And now on this side I'm going to factor out the second velocity squared and divide by the remainder. So I get 26.784 joules all over. I factored out the v2 squared and I'm dividing by what's left over. 0.7 kilograms squared all over 0.25 kilograms plus 0.7 kilograms. And again, that's equal to v squared, so you take the square root of both sides, you get v2, you plug this in your calculator, you get a value of 3.17 meters per second. So that's the mass of the second sphere. Now I have to determine the mass of the first sphere. Again, using this equation, which I will bring over here, we know that V1 is equal to V2, which is 3.17 meters per second, times mass 2, which is 0.7 kilograms, over mass 1, which is 0.25 kilograms. Plugging this all in yields a value of 8.89 meters per second. And for part B, if the spheres were conductors, the charges would be polarized across the spheres, with a negative charge lumping towards the right side of the first sphere and the positive charge lumping towards the left side of the positive sphere. And this results in the charges being closer to each other. This results in a greater force, which results in a greater acceleration, therefore resulting in greater speeds. It is important to note here that the smaller sphere has a higher speed but a lower mass, and the second sphere has a lower speed and a higher mass. And this makes sense because of what we derived right here, that the change in momentum is the same, since the change in momentum is mass times the change in velocity. Side note, I also figured out another way to determine the amount of work here. You could use the equation work is equal to negative the change in electric potential energy, and using our equation KQ1 Q2 over R, you could solve for the same value, but then you don't get to take an integral, and there's no fun. When I was first doing this problem, the challenges I ran into were figuring out how to determine the amount of kinetic energy in the system, and I figured out you could do one of two ways. And then my second problem, once I got to this stage, was determining the ratio of the first sphere's velocity to the second sphere's velocity. And I realized that since the forces are equal, they have to have an equal momentum change. And I realized I was able to manipulate that to get a ratio for the velocities, which I could plug into here and solve. And this problem shows my growth as a physics student because it shows that I understand the electric force and how it's attractive between charges of opposite sign, and it shows that I'm able to accurately integrate in my equations to solve for numerical answers. Also, it shows that I did not forget from last semester all about momentum and how work is the change in kinetic energy. Thank you.